Hi everyone, today is going to be your third lecture of this week for this semester. The topics are primitive unit cell, Wigner-Seitz cell, and conventional cell. And at the end, I will talk more about common crystal structures. Let's take a look at the definition of primitive unit cell. What is the definition? So it contains only one point. I will show you in the next slide how I mean by only one point, okay? And it has a volume that is independent of the choice of primitive cell. For any pair of different primitive cells, one can always subdivide one of them and by translation through lattice vectors, assembly it into the other primitive cell. So the volume is independent of the choice of primitive cell. We'll show you in a minute. Here are all examples, right? So let's say this is like a 2D. So let's read this out. A region of space, area 2D or net, or volume 3D or Bravo lattice, right? That when translated through all the lattice vectors in a Bravo lattice or net, fills the entire space without leaving voids or overlapping itself is called a primitive unit cell. Remember that last lecture we have learned how to build up the primitive vectors for simple cubic, BCC, and FCC. Here it's like in general pictures, right? So how do they say about all these primitive unit cells fill the entire space? So I make you a drawing. This is a primitive unit cell. Imagine it's just like a stamp, right? Like that, okay? And then you move the whole thing here, okay, next to it. And next to it, left, right, bottom, top. And notice that what? They all fill the entire space, right? Same as this set of the primitive unit cell. Same, fill the entire space without leaving voids or overlapping itself. Same as this shape, right? And notice that all of these, what? Contains only one point, right? In the cell. And the similarity is that all the primitive unit cell that we pick up for each case didn't leave any voice, right? Or overlapping itself, okay? And again, each cell, right, primitive unit cell contains only one lattice here. Okay, so move to primitive unit cell for BCC. For simple cubic, it's easy, right? For simple cubic, because A1, A2, and A3, which are primitive vectors for simple cubic, they all perpendicular to each other. So when you build up, it's gonna be just itself, right? But for BCC, it's not that, okay? Let's look at the symmetry one. Okay, remember this figure that you have learned from last slide. Notice that I wrote this down, that the primitive unit cell for BCC is only like half, right, of the volume of the conventional cell. So this is the conventional cell, a cube here and a cube here, or a cube here, or even a cube here, okay? But let's take a look at primitive unit cell for BCC, how it looks like. So go back to the last lecture. We have learned that we have A1, A2, and A3 like this. So this figure is not the same as this, but actually, like if you change the origin from this point, right, the corner that like face to you to here, okay, and X, Y, Z, when you make up the axis, gonna make sure that you follow the right hand rule. X cross Y is Z direction. So let's review again. A1 is 1/2 A minus X hat plus, in the parentheses, Y hat plus Z hat. So what does it mean? Remember this? You have learned from high school already, right? So let's check this out. A1, the prefix in front of X here and with minus, that means the projection, right? So this is minus X axis, go that way. So if you project this guy here, right, it's gonna end up on the bottom, okay? And the projection on Y, okay, I write the Y first. So the projection on Y, you can see it easily, is 1/2 here, right? This point, and projection on minus X, right? Gonna be A/2 as well, but it's minus. And how about Z, right? The projection is with the length of A/2, right? So this one is A/2, and here is another A/2 here, okay? The rest, can you try to do by yourself? Okay, I show you maybe a little bit for A2. So for A2, right, if you project it on the floor here, right? This projection, make sure it's perpendicular. This is perpendicular here, right? This is perpendicular, okay? So if you project on this surface at the bottom here, on this plane, X, Y plane here, you're gonna get this length A/2, right? But right here is another A/2, but with the minus sign, because Y-axis is go minus Y-axis, right? go that way. Okay, and C. This is again same number, a half. Okay, so try to think about this by yourself. Okay. Okay, good. So next, how to build to have the primitive unit cell for BCC. Okay, we have A2 already, right? So now we build the length that is parallel to A2, right? Parallel to A2. Okay, good. Now A1. Or you can like translate all these three vectors, right? All around the space. So you connect one lattice to another and parallel to A1. So you have something like that, right? And A3, okay, this is purple. Oops. Okay, let's try again. So from here to here, parallel to A3. So this A3. Okay. So here we go. We have the primitive unit cell for BCC. Next, primitive unit cell for FCC. Remember this figure from last lecture. Again, primitive vectors for FCC. A1 is 1/2 A on this plane, YZ plane. So this is YZ plane. So this is like, it's just in front of you, right? If this is a cube. So A1 is pointing here. Just imagine that the projection of A1, right, on y-axis is A half, and on z-axis is A half. And how about in X? No projection, right? Because it's on X, Y, Z plane, okay? Can you think the rest by yourself? Okay, great. So move on, here is the same picture, right? But here is the model that I have in my office, and I highlighted with green here. It's the same. A1, A2, and A3. Okay. And how do we build this? Let's be redraw this. So this is like A1, right? This is A1. So you will see that you try to build, right, something that is like a parallel to A1, right? And how about A2? This is A2. A2. This is A2. from here to here, right? From here to here and on the back, like that, right? And same as A3, A3, right? Oh, this is A3, sorry about that. This is A3. So from the one at the middle here, right, to this. So this A3 and A3, right? Okay. So if you combine all these, right, combine all these, you're gonna end up with this shape, this figure. Okay, great. So next move to another kind of primitive cell. Is particular, okay, particular primitive cell with the full symmetry of the lattice. Remember that primitive cells are not unique, right? This is a special one, but with full symmetry of the lattice. But remember, it has to contain only one lattice point. So let's see how we build. First, you draw lines connected to one point to all others. So imagine like we focus on this point, right? And then you draw a line. So here is all the dotted line, right? So if you are at home, make sure you have a ruler, a pen or a pencil, and then draw a line like this, okay? And then we do this. We draw another line, right? Bisecting the dotted line that we just draw. How do I mean by that? Okay, so it's like this. For example, I have this. So when I measure this length, right, I said, okay, this is half, right? This is half of this dotted line length here. And then I use a ruler to draw this line. Okay. Do the same. So half, this is half here. Then you use a ruler to draw a straight line perpendicular to it, right? This is perpendicular to this, okay? Where's a half? Half is here. Cut it like that, okay? Half of this length is this. And half is this. Almost done. The last one, right? Dotted line here. Measure halfway. And then draw a line that perpendicular and bisect. Okay. Great. So we will get at the end the smallest polyhedron or polygon that encloses the point bounded by the planes or the all these lines. Okay, so this is called the Wigner-Seitz cell. Okay, this exercise I will leave it for you to do as maybe exercise during the class. You can pause this video and try to see it's a different arrangement of all these atoms. Okay, let's move to Wigner-Seitz cell for BCC. Okay, BCC, remember 8 corners contain 1 atom or 1 lattice point at each corner. So we have 8, right? Top we have 4, bottom we have another 4. So we have 8 atoms. And in the middle, we have 1. So how to build the Wigner-Seitz cell is very simple. So we draw a line, right? Like a diagonal, go to all the 4 atoms that sitting at the 4 corners of the top surface, okay? And another one, 4, right? To the bottom at all the 4 corners of the bottom face. Now imagine that you have, okay, here I draw this one. So it's the same as this guy, right? So now imagine you have another cube, right? Sitting on top of this. Okay, and in the middle, you have another atom that at the center of the cube, right? And then remember you draw a dotted line, right? And cut half. Okay, so this is gonna be this surface once you cut it, right? Yeah, if you want, you can try to see. Oops, sorry. If you draw up, right? Have the atom sit on the cube, right? And here also to the front, it's like this, right? And then you make a dotted line and cut half. Okay, so when you cut half, you're gonna get this surface here. And then do the same here. And here, right, next to it, all around here. So this, again, cut half, right, you get this surface. Okay. So now, if I ask you, how many faces do we have for this? Can you help me counting? So imagine this, we have like 4 sticks, right? Pointing to all the 4 corners. So we have 4 faces already, right? 4, 1, 2, 3, 4, and plus another 4. So this is top. So this is bottom. Another 4, we have another stick, right? 1, 2, 3, 4, and then you cut half. Okay, so 4 plus 4. And then around here, remember, in the middle here, the red atom here will point, right, 4 faces. 4 faces, right? 1, 2, 3, 4, right? 4 faces. And this, okay? Another 4 here on the sides. And another 2. 2 is like 1 from top. And this is another one at the bottom. Here, so this and somewhere here that you will not see, but you can see from here a little bit. So total would be what? 14 sides. The polygon with 14 sides. Okay, great. Next. Wigner-Seitz primitive cell for FCC is a little bit tricky. So now we have to maybe sit on somewhere else. Okay, so we sit on the side, right? Okay, or on the face here. FCC again, 4 at the top corners, another 4 at the bottom, right? Bottom surface, and at 4 corners. So we have 8 and another 6 because the cube has 6 faces, okay? The red atoms here are the red lattice points that I make the color red here. Look at this, it's like in the same plane, right? So this is the same plane to help you visualize better. Okay, so when you draw it, right? Okay, we sit on here. When you draw it, it's gonna be from here to here, to here, and to here, okay? And then you cut half, right? Cut half, half, and half. Next, go to the blue one, right? The blue one. From here, top, bottom, from here, right? Top and bottom, and then cut half, cut half. Okay, and somewhere here, you will imagine that you will have the box, right? Next to it, and the atom is somewhere here. So from here, you point like that, okay? And then cut half. And another one here. Like that, okay? And cut half. So imagine you have another box next to this side, okay? So that if I can color it for you, so be like this guy, right? And this guy. And then on the front and on the back also, right? On the front and on the back. And notice that the green one, right? The green one is on the same plane as the blue one, right? It's on the same plane here. And then you draw again a line, right? Here from here to here and cut one half, right? So at the end, you're gonna end up like this, okay? Okay, how many sides now? Can you think by yourself? How many sides? We have 4 sides, right? On the top, another 4 sides at the bottom, and another 4 on the sides, right? 4 plus 4 plus 4 is 12. So total will be 12 sides. So the polygon with 12 sides. Okay, so this is, I found a video clip that maybe with different orientation, maybe it will help you to visualize a little bit better. Okay, this is a model, right? We already have seen this. So this is a model that you will see the 4 sticks on the top and another 4 sticks at the bottom plane, right? And on the sides in the middle also, okay? So maybe that might help. So let's take a look at these pictures again. So I found this one may be useful for you to memorize better. So for BCC, Wigner-Seitz primitive cell for BCC, we get truncated octahedral. Octa is 8, right? Octa is 8. Set is 8. This is 8, right? Why is 8? Imagine this. So this side, and this side is like you have the pyramid glue to another pyramid. So we have the top like that, right? And the bottom like that, right? So this is like a 8 sides, right? Octahedron. But truncated, that means like at the peak, when you cut it, right? When you cut it, it builds up this shape. So when you cut the bottom, when you cut the peak of the pyramid. So if you cut it, right, of the pyramid, you will end up with this shape. Same as here, right, above here. And at the top surface, you will see the same shape, okay? That's why it's called truncated octahedron. Okay, so now let's see our Wigner-Seitz primitive cell for FCC. So maybe this one a little better view. Also, if you cannot follow the picture that I had in the last slide, okay. Okay, great. Okay, what is conventional unit cell? Like I said, it's non-primitive unit cell, but it's convenient for your eyes, right? Convenient for you to pick up easily, okay? Or it's like you see that it's like, oh, easy to remember. It is not like weird shape or things like that. Typically, these unit cells have a few times the volume of primitive cell. Remember, primitive cell contains only one lattice point, right? So of course, primitive cell has the smallest volume compared to the conventional unit cell. In the next lecture, we'll talk more about this, okay, the 7 crystal system and 14 Bravo lattice. Let's talk about some common crystal structures. The first one is called close packing. So close packing, we have 2 ways of building it. Okay, 2 ways of building it. So I show you this one. Okay, so if you have coins in your pocket or in your wallet, get them all out from your wallet and then try to build it with me. So we will build AB, AB, and another one, ABC, ABC. So when you build, right? So this is your coin. Should have the same size. So you put all the coins like this. Okay. So this is at the bottom. Now to build A, okay, so we have done A. So this is A, right? And then next, you put on the second plane, right? Top of the bottom. So you put your coin like this. Okay, can you try to do by yourself? And the third one, so I'm gonna use orange then. The third one, what you have to do is like, it's gonna be like this. So this is another A, right? On the third row, okay? On top. So this is gonna be A, B. So this is B. And another A. So this is A, B, A, B. Okay. How about A, B, C, A, B, C? C, let's see, C. Let's make it green. So notice this. I have to draw this for you. So this form like a triangle, right? Triangle. So for C, right, you will build up the third row that have the triangle that is flipped from this. It's gonna be like that. Okay. So the picture will be like this. Okay, I think if you use the coils, I mean, you will see it better here. Okay, it's just like this, and the bottom it form like this pink. Okay. Let's draw pink for you here. From here to here to here. So this is this. Okay. Redo it with a straight line better. Okay, and top one, right? Is this and this. It's gonna be like that, right? Something like this. Okay. Okay, great. So let's take a look. So simple hexagonal Bravo lattice, right? So when you form something like this, you will know this angle is 90 degrees. And if you have another plane, right, in the middle of these two, and you will see that when you build A3, so this is, this is A3 here. So when you build another R here, or the vector here is gonna be A1 third, A2 third, and A3 half. So this cut half here. Okay, great. So close packing, we have AB, 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 and ABC, ABC, ABC. Okay. AB, 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 we sometimes called hexagonal close pack. Okay. So this is in 3D. And for ABC, 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 we call it like a close pack has sphere with FCC, because from this figure, if you cut this, right, to make a cube like that, right, it just looks like FCC. In this table is an example of the hexagonal close pack. This is a types of crystal, and this is C over A. Okay, good. So next, move to diamond. So diamond, if you see, right, it just look like FCC, right? I mean, if you look at only all the black atoms here, and inside, right, inside we have also the other atoms that the projection. So this one is the projection of the C projection. Okay. And What is the difference between diamond and zinc blende? Diamond contains all the positions with carbon atoms, and for zinc blende is not. Okay, zinc blende is not. Maybe you guys might not familiar. I mean, some examples of zinc blende. So I will leave you to do as your homework. Okay, so find out some examples with zinc blende structure. Okay, I will give you one example. Could be cadmium sulfide, right? Or even another example, gallium nitride or gallium arsenide. Okay, so think about some more. Okay, and if you have more time, look for the applications. It's really like practical for a lot of zinc blende structures. Okay, great. So move to sodium chloride. So this is maybe the crystal structure that you have seen often in your chemistry class. It's just like rock salt, right? Rock salt. If you see only the blue, okay, only the blue. Look, only the blue, right? Only the blue. It just look like what? FCC. And if you shift it to half, okay, shift it to half and look at only the white. So it's like another FCC. So it's like you can think of this way. It's like two FCC printed, right? I mean, like overlap at the point half of the cube, let's say. But notice that the size of sodium ion is smaller. Sodium ion is blue, smaller than that of chlorine, okay? And this is all the positions or the coordinates of the sodium. So for your homework, okay, this one I give you what? I give you the Z projection, right? So your homework, you have to find out what is all the coordinations for each atoms, okay, for zinc blende. That means you have to know what X, Y, Z, right? Same as this, X comma, Y comma, and Z comma. This is some examples of types of crystal that has the structure of sodium, similar to sodium chloride. Could be like sodium iodide, like that, okay? Cesium chloride, so the cesium will be in the middle of the cube, right? And chlorine will be at all 8 corners. Some examples of this is like this. Okay, great. Okay, so we will finish this lecture for today. It's quite long, and I will see you again next week. Okay, hopefully I can try to get to show you some models in 3D, and maybe it will help you to visualize some that maybe for you, if you see in 3D, maybe it's gonna be better for you to imagine or visualize a little bit better than seeing it on 2D plane. Okay, so thank you for listening. So I'll see you next week. Bye.